passes through the circuit, there is a change in the EMF that is being generated because of the variations in the temperatures that we are. And similarly, we also have Thomson effect. Be careful to understand this. In the Thomson effect, what happens is if there is a temperature gradient across the wire, then automatically there is a change in the EMF. There is a temperature gradient, that means the temperature keeps on changing along the wires, then obviously we also have an electromotive force change that is being created. That is basically what we call it as Thomson effect. Okay, so now we can understand that in a thermocouple circuit, we don't want to have electric current passing through it. Okay, therefore the effect of Peltier and Thomson effects are being negated. These two effects we are actually taking it. Okay, if they are there, then automatically whatever we are getting from the thermocouple circuit is basically we are getting an erroneous value. Okay, so that's why we are trying to negate we are not allowing any current flow through the circuits. The Thomson effect, when there is a temperature gradient, we also have when the temperature gradient across the wires, then obviously we will have some kind of EMF that is being altered because of that, and that is called as the Thomson effect. So the main thing that we look out for here is we want a high input impedance measuring instrument to measure the voltage that is created in the particular circuit. Okay, so we don't want the errors because of current passage. We have voltage variations which actually creates error in the final measurement. So we don't want that to happen. So therefore, we will always try to have as low current passage through the circuit as possible. Okay, so that is what the Peltier and Thomson effects are, and we are trying as in thermocouple circuit, we try to eliminate these two effects. Therefore, we generally maintain the temperatures only varying at two different junctions, and then whatever the EMF that is being generated, we try to measure that, and from that we will try, by knowing one of the junction's temperature, we will try to find out the other junction's temperature. This is in short what is temperature measurement by thermal. So by now you might have understood that the electrical current passage because of the Peltier and Thomson effects will actually alter the variation, and therefore it is our responsibility to see that the Peltier and Thomson effects are not there in the circuit. So this part we have already discussed, that the delta V, the potential difference of the electromotive force that is developed, is directly proportional to the temperature difference. The more the temperature difference between the junctions, the more the electrical difference. So which is also dependent on a particular value of the property of the material, which we call it as Seebeck effect, which is defined here, S of T, that is the Seebeck effect or Seebeck coefficient. We have discussed about different kinds of mostly used thermocouples and on which materials they have been fabricated, and then what is the temperature range in which they work properly. And what are the advantages of thermocouples we have seen, and what are the disadvantages of the thermocouples also we have. So now we will go on and look at the thermocouple circuits actually. So the figure that we are showing over above shows that the measured output voltage. So that means we have metal A, so this is the metal A, and we also have metal B, which is an open circuit. For example, it is not closed circuit. If we keep some kind of a closed circuit, if we close the circuit, then electricity will produce. So what is happening over here is basically we are only not closing the circuit, but we are trying to put a voltmeter and find out the voltage difference. That is what we are trying to find. So we are trying to measure the output voltage, which is nothing but, which is another way we can say that the difference between the hot and the cold junctions. Okay, since VH and VC are generated by temperature difference between the two junctions, V out, that means the output voltage is also a function of this temperature difference. So why this VC is coming? Because of this variation in the temperatures. Why VH is generated? Because of the temperature in the two decimal point. So remember, if it is a material with different temperatures, one temperature is here and another temperature is here, if it is a single material, we will not have any electrical or electromotive force that is being generated. Only heat energy will transfer. Since we have two different materials and are maintained at two different temperatures, we have an EMF is being produced. Okay, so in that way, in that sense, the scale factor, whatever you are keeping over here, A, which relates the voltage temperature difference to the temperature difference, is what we are calling it as Seebeck coefficient. Okay, clear. So now, what are the major things that we have to keep in mind while working with thermocouples? You must establish a reference point. Okay, so you have to know precisely the temperature of the cold junction or the hot junction to find out the other thing's temperature. You must establish a reference point because thermocouples are basically defined on the differential temperature measurement. Basically, they comes under the classification of differential temperature measurement device. So we can only find out delta T from the delta V. The change in voltage because of the change in temperature is what we all can measure. But without knowing one of the temperatures, we cannot find out the other temperature from the change in temperature. So it gives only the differential temperature. By knowing one of the temperatures precisely, we can try to evaluate the other temperature. Again, a thermocouple that actually provides a voltage which represents the temperature difference between the hot and the cold junction. What is the voltage difference that is representing? It represents the difference between the two hot and cold junctions. So now, if you know both the temperature of the cold junction and temperature of the hot junction relative to the cold junction temperature, you can determine the actual hot junction temperature. So this is the same redundant statement. I don't know. So now, when the two dissimilar materials are connected to a measuring device, there will be another thermal EMF generated at the junction of the materials and the connected device to the voltage measuring instrument. So when these two dissimilar metals we are connecting to a measuring device like voltmeter or other thing, there will be another thermal EMF generated at the junction of the materials and the connecting device to the voltage measuring instrument. So we are trying to connect this to measure with the voltmeter or any other potentiometer or anything. So there are extra wires that comes into picture, and because of that there is another thermal EMF that is being generated, or the voltage, another voltage or extra voltage, that is because there is another material which is actually connected. So we need to understand that these are not only two junctions, but we also have another two dissimilar metals which are actually connected to the measuring device. So that will create unnecessarily extra voltage difference. So we have to find out what is that extra, or we have to make sure that that effect is also measured such that we will actually find out the true voltage difference. Okay. Have you got what I'm trying to say? What I'm trying to say is simple, that we have a material A. Let us say this is a material A, and this is connected to, at a junction here, we have connected to a material B, for example. This is B. And this one I am taking over here, and this one I am taking over here. And these two ends, instead of this way, I will try to find it A, and this is B. Let us say that this is open. Right. What I'm trying to say is, this material is like this, and this is one junction for which we are connecting. This is A material, this is B material. So this is open end. Similarly, there is another junction that is created here. This is B material. This is the junction over here. This is the junction over here. And this is the open end. This we have to connect to a circuit, close it. So A material, when we have two junctions, this is hot junction, for example. Hot. This is, let us say, this is a cold. And I know cold, so therefore delta T dependent on the voltage difference, I can find out the hot junction. So now if I want to connect it to a measuring device like voltmeter, I am again connecting it to a another wire and another device, correct? So for connecting to this device, I am using another wire. For example, let us say that this is copper or something. So because of this two different materials and two different junctions over here, we are also having another EMF added to the, for example, when this is not connected, we have EMF1, and because of C, this is for A and B, and we also have another EMF that is being generated, EMF2, for B and C. So if we can find out what is EMF2, which is actually induced because of this measuring instrument, we can safely find out what is EMF. That is the whole crux of this particular statement. Am I clear? Any doubt in this? Okay. So now, for understanding this, we have certain rules for the analysis of thermoelectric circuits. We have certain rules for the thermoanalysis circuits. For example, the very first one is the law of intermediate materials. Law of intermediate materials. Suppose this law deals with the different kinds of materials that we use in a particular thermometer or thermocouple circuit. Okay? The net EMF of the circuit, whatever the EMF that is induced between these two circuits, where any number of dissimilar materials are introduced. So you introduce any number of dissimilar materials, remains the same. It remains the same. It will not change as long as the new connections are at same time. For example, you have material 1, you have material 2. Initially, you can understand that the material 1 is connected here to with a junction to material 2. Similarly, we have one material. Similarly, you can take another junction, we have another 2. Okay. Now, instead of this circuit, what I am trying to do, I am keeping another material I am adding. This is 1, 2, third material. This is the material 3. If the material is connected to material 1 and material 2, for example, if you want to connect this, so what happens now? We have 2 more junctions that are created. Until and unless the temperature at junction TC and the temperature at TD are same, both the joining or the junction at which the third material is connected with 1 and 2 are at the same temperature, then obviously there won't be any change in the EMF. The EMF will not change. No matter how many materials you induce. Material 1, material 2, material 3. So material 2 and it is connecting with material 3. And finally we have material 4. This is material 3, material 2, this is whole 1. If you measure the voltage when T2, T3 and T4, whatever the T5, if all the junctions temperature T2 is equivalent to T3 equivalent to T4 equivalent to T5, so no matter how many materials you join, doesn't have any net EMF. It will be the same. It will not create any extra EMF in the circuit. This is what we call it as law of intermediate material. That means if we have a variation in the temperature, then obviously this EMF will be affected when a third element or material is introduced into the material. I hope I am clear. Okay, so that is the other side of this. Clear? Now, law of intermediate temperature. Suppose we have only dealt with what happens if we have different materials inscribed into the different materials. If we increase the number of materials with junction temperatures remaining the same, then there is no change in the EMF that is being. Next one is law of intermediate temperatures. What does this tell you? For example, we have 2 dissimilar materials like T1 and T2. So one is this junction T1 and there is junction T2. So one material and the second materials are joined together. Okay, and then they formed 2 junctions which are maintained at 2 different temperatures. Because of that, the potential difference that we have created is zero. So the EMF force, electromotive force is capital E1, is what the potential difference that is created. Similarly, the second material and another third material I have made into an thermocouple kind of thing, where because of this T2 and T3, because of the change in the Seebeck coefficient, we have an electromotive force which is E2, which is other than E1. For example. Now, suppose if I am making another thermocouple with T1 and T3, then obviously the electromotive force that is being generated, that E3, whatever electromotive force is generated, is nothing but the summation of the E1, which is because of the electromotive force generated because of the joining of two materials 1 and 2, plus the EMF generated by the joining of two different materials T2 and material 2 and material. So this is the law that says that even though you have different materials joined together and the final net input, net EMF is dependent on the materials that you are trying to join. So this is basically your law of intermediate. So the variations in the temperatures T1 and T2. So there are two different temperatures. Here T2 and T3, we are getting T2. Now, if you are directly going maintaining the temperatures at T1 and T3, if you are maintaining the temperatures at T1 and T3, which is not in between T2, it should be equivalent to the EMF that are produced with T2 and T3, T1 and that is what it means. So even though the materials remains constant, the junction's temperatures are varying. So be careful. Here we are changing the materials differently. The junction temperatures are kept constant. We are not varying Tc is equivalent to Td here. Even though the number of materials you vary, the EMF will not change. Whereas here, the materials are same 1 and 2, but the junction temperatures are varying, not the materials. Okay, if I'm conveyed it is wrong. What I'm trying to convey is the materials are same. This is 1 and this is 2. Two different materials, but the junction temperatures, initially the first temperature is T1, here the temperature is T2. Similarly, in the next case, the one of the temperature is T2 and another temperature is T3. Because of that, we have E1 and E2. Now, what we are trying to find out is one of the junctions is maintained at T1 and the other junction is maintained at T3. So whatever E3 that I am getting is nothing but the summation of the electromotive force generated with T1 and T2 as junctions and T2 and T3 as another junction. So these are the basic rules that we follow in thermoelectric circuits. These are very important for the exam. Okay. So what is the commonly used thermocouple circuit? So as I told you, you are using the circuit over here. So how do you measure the thermocouple circuit? We are giving an example where the open ends of each wire are electrically connected to wires made of copper. You can see over here, this is metal A and this is metal B, and we are making one junction over here, which is the hot junction, and there is another cold junction where the temperatures of this and this, if they are different, again there will be a different EMF being. Therefore, the junction temperatures here as well as here, they both are same. I'm talking about this junction, this whole junction where the terminal points, this and this, if they are at different temperatures, obviously we have different EMF being produced, erroneous results become. So here we are trying to make the temperatures as same, and the ends of it are we are connecting to a copper wire which is connected to the measuring device, which is connected to the. Since the temperature of here and here are same, it is not varying, correct? Since these temperatures are not varying, the output voltage will not have any EMF generation. The generated EMF is equivalent to the difference between metal A and metal A, law of intermediate materials. So this is what we generally use for thermocouple circuit. Are you with me? So are you understanding what I am trying to say? What those physical principles that we understood are basically applied here to measure the basic temperature. So we have two junctions. So in practice, how do we incorporate them into our measuring devices? We have one junction where we are entwining them, but we are turning, twisting, or we are basically what we are trying to do is welding kind of a thing, or what electrical terms, what we call it as the welding small thing. We have studied in your basic thermal engineering, basic mechanical engineering. Soldering is the process. So by doing a soldering or by means of a micro welding, what we do is we make a junction over here. We are trying to make both of them as well. But the ends are connected to the terminals where the temperature is maintained constant. And again, we have another third material which is actually connected coming into the circuit. But the ends of the two materials are connected at the same temperature. Therefore, we have a output voltage, which is the result of the junction temperature between metal A and metal B, and it doesn't include anything related to copper. Okay, so that is what I have mentioned. As long as these two junctions are at the same temperature, the intermediate metal copper has no effect on the output. Okay, so this configuration allows the thermocouple to be used with a separate reference junction. Therefore, it helps us to use that as a separate reference junction. So therefore, Vout, that is the output voltage that we are getting, is nothing but the function of the difference between hot and cold junction generation related by the Seebeck coefficient. What is the Seebeck coefficient? A, and the relation between TH minus TC is nothing but Vout is nothing but the function of this TH minus TC, the difference in the hot and cold junctions, along with the Seebeck coefficient. So this is what we are trying to put in a data logger thing also. We will try to form this junction. This junction we are creating on an unknown surface where we want to find out the surface temperature. The other ends we are connecting it to a terminal over here. Okay, where the terminals are maintained at the same at room temperature. And then the internal windings will create this as a reference junction temperature. And this copper wire will be inside, and that electrical circuit will help us to find out the potential voltage difference between the. Any questions?
Sir, there is one question in chat box, sir. How do we calibrate thermocouple circuit?
How do we calibrate?
Thermocouple circuit.
Thermocouple circuit, you are actually trying to know the value. So you answer this question. You try to answer. How do we calibrate? So one of the thing is you should know the temperatures, right? Right. So we have, suppose the thermocouples are there. Okay, let us discuss this. We have the thermocouples. Okay, we have bought straight from the market. We have got the thermocouples, and by having an instrument where we can bond the two ends or one end of the thermocouples, I'm trying to put figure, but it will be very different. So I bought one wire. Okay, one wire which is having two wires inside. And this is how the thermocouple, and there is a sheet, a covering of this will be there like this. Okay? So inside two wires are there. For example, you imagine that this wire is like this. There are two terminals like this. Okay, what I'm trying to do is these two terminals, I am trying to make it into one simple bond. How do we do that? We do that by welding or soldering process. So the welding machines will be there where you apply high voltage, and therefore the electric current will come, this melt this temperature, and then they both are joined. If you allow that to cool down, it will be forming a bead. This we call it as a bead. Okay, now I want it to get connected to a different. So we have this what we call it as data logger. I will show you what I have a data logger. I will just show you. It's a very bad figure. I don't want to show that. Here is this. Can you able to see my screen? If you pin my screen, it will. I'll stop presenting. You can see my screen, I think. Yes. So now you can see this is the thermocouple that I'm talking about. This is a thermocouple where you can see that these are the two ends, two wired ends, two dissimilar materials. Okay, two dissimilar materials. They both should be formed as a junction. So in manual I'm doing, it may not form proper bead like this. So you can see here there is a black thing that is actually the bead that is actually formed because of the soil. The other end, you can see the other end is left over, right? The other end is left over. Now I'm showing you the basic data acquisition system or data logger that we have. I don't know, the battery is working. This is the data logger that I have, okay, which is a portable one. So what I can do is, you can see the two terminals over here. Yes. So now one end of it is connected here, one end of it is connected here, another end of it is connected here. Okay. So the internal circuit that consists of it will form the zero temperature compensation. We call it as zero temperature. So the reference junction is this. This one creates the reference temperature as whatever cold junction we are talking, that is created within this by electrical device. Clear? So now one end of it is connected here, and we know what is this. For this time being, you understand that we know the temperature of this particular device here. Okay. You know this particular temperature of this here. Now, wherever the unknown temperature, the question that you asked is basically how do you calibrate it? Now you know you are connecting it to the data logger, one end. Other end is bonded, and that you will keep it in a temperature bath, what we call it as. We call it as a temperature bath, which can be precisely controlled, the temperature of the water within this tub or tube, which will be connected completely, which can be controlled from 0 degrees centigrade to approximately 80 degrees centigrade. Our sub temperatures also we can do. Okay, we call it as Julabo. You can write it down, JULABU. That is one of the mostly used temperature bath, JULABU. That is a company that produces very precise temperature baths. So we have a cold junction temperature compensation that is created within the device, and we have another junction which is we are keeping it inside a carefully controlled temperature of water, where we can control the temperature of water precisely. So we keep that in that, and we also have an RTD which can measure the temperature of the water very accurately. Now, by switching on the electric current, by using a heater or by trying to cool the water or heating the water, we start with 0 degrees centigrade. And the thermometer which is kept inside, which is RTD, which may be RTD or any other precise device, which actually measures the temperature of the water. And a thermocouple, because of the connection, one end of the bead where we have made a junction, we kept it inside the water. So because of the temperature difference between the cold water and the junction within the data logger, we have an EMF that is being produced, the voltage is being produced. That is measured by the data logger. So we will note down the voltage, whatever the voltage that we have. Actually, that will give you, there is a voltage component that will actually convert that into a particular temperature. If you mention what is your thermocouple type, if you mention the thermocouple type, it will show some temperature. We know the reference temperature from a precise measured device RTD. We know actual temperature of the water, and there is another device which is actually measuring the temperature because of this thermocouple, which may be slightly different from this. Suppose if it is showing, for example, 10 degrees centigrade, it may be showing 10.3 degrees centigrade or 10.4 degrees centigrade. We will note it down. Actual 10.3, output 10.3. We will increase slightly, 15 degrees, 20 degrees, 30 degrees. Likewise, up to 80 degrees we will measure. So what is the other fluctuation? X we will write down, output we will write down, we will make a graph. From that we will get a calibration curve, which is mostly linear in nature. For thermocouples, we don't get exponential or another profiles we don't get. In general, it will be a linear, like a straight line with some slope. So we will take that value and we will keep it into the, we can give that slope, what is our slope and what is our y-intercept indirectly into the instrument. So therefore, it takes care of the other things. It will automatically, now, if you put the bead onto some unknown temperature, automatically it will calculate, find out what is the difference, and then gives you the exact value. Am I clear?
Yes, sir.
Yeah, is it clear now? So that is
Yes.
it.
Yes, sir. Yes, sir.
So let me continue with this. So that is very important. How do you do a calibration with the thermal this thing? So that's the same thing that I have talked about here. Next, we will move on to the next topic, which is conventional reference cold junction. So how do we use conventional? The same thing. What initially, how do they measure the conventional cold junction? How they used to maintain? In the early days of thermocouples, when they started using the thermocouples, ice bath reference. So we have the ice as well as the saturated water at 0 degrees centigrade. They both are kept in a kind of a Dewan flask. We call it as DEWAR. Dewan flask we call it as, which is highly efficient flask, which can keep the temperature of this ice and mixed together with water for a long temperature. For a long time, they can keep the temperature at 0 degrees. So that was what we used to use in the older days. Okay, that uses as the reference junction in the bath, ice bath. So you can see over here, this reference, whatever is shown here with ice and mixed with some water at the same temperature. So this is evacuated, or this can be, this is well insulated from the surroundings, okay, by a suitable flask or something. So therefore, the temperature is maintained within the junction at 0 degrees centigrade for longer times. This is the standard procedure by which we were using the preparing the ice bath or cold junction. Whereas this iron and constant and other bead is kept at a place where we want to find the temperature, unknown temperature. And these two are connected to the junction here, which is at the same temperature. So therefore, EMF can be produced that can be used to find out. Okay, so therefore, when the cold junction is not at 0 degrees centigrade, the temperature of this junction must be known in order to define the actual problem. Suppose the question is, sir, what if we cannot maintain this temperature at 0 degrees centigrade? The question is simple, the answer is simple, that if it is not maintained at 100 degrees, 0 degrees centigrade, what is the temperature you are maintaining? Are you maintaining at 10 degrees centigrade? You should know the exact temperature of this cold junction, or you should know exact temperature of, since this one is used for measuring the temperature, we have to know this temperature precisely. That is what the bottom line is. You maintain at 10 degrees or you maintain at 5 degrees, that doesn't matter. The more the variation in the temperature, the more the EMF. And generally the EMF produced is in microvolts, right? So it is 1 by 1 millionth of the volt. So that's why it's a very low value. So in order to improve that, we generally want to have higher temperature and readily reproducible temperature. Why 0 degrees centigrade? Why not other temperatures? Because it's very easy to reproduce the 0 degrees temperature compared to the other degrees temperature. Okay, so they are just phase change kind of a thing. So generally, for any standard procedures, why we go for that is basically we can reproduce the same state again and again very easily. That is the reason why we go for 0 degrees centigrade. There is no other possible reason that I can think of. It's the reproducibility of the temperature or the state of that matter is what makes is what keeps that 0 degrees as the standard. Nothing else. Okay, those are the two reasons that I can possibly think of. Now we have cold junction compensation. We think we have got this iron constant and thermocouple, and then we have this, and then we also have this copper extension. As I told you, when the temperature of this are at the same temperature, the EMF will not change. Okay, but if it is non-zero, suppose the temperature is non-zero, it has some various other temperatures. So the output voltage, whatever we are getting, is having the effect of this non-uniform temperature at these junctions. At these two junctions, whatever the temperature difference, that will also create some voltage. So in order to measure that, we need to have a what we call it as cold junction compensation. So the cold junction is not at uniform temperature, but it has slightly different at the T2 connections, at the two connections. Therefore, we have extra EMF being produced. So we need to know what is that extra thing that is created. So what can we do is we can produce this cold junction compensation, the extra cold junction compensation, by having an IC, thermistors and RTDs. We will come back to what do we mean by RTDs in the next class. These are all the thermistor and RTDs are the temperature measurement, direct temperature measurement device. I mean to say direct means it's like a thermometer only, okay, but more accurate. So either a thermistor we will use or an RTD we will use. These are two different temperature measurement devices. So we will use them to actually measure the cold junction temperature. Okay, so that will help us to find out the cold junction compensation. Okay, after knowing this temperature, from the output we will take out this cold junction this value such that we will get back to the question. Now, these are the general conventional methods what we use for establishing reference temperature in thermocouple circuit in general. So you can see over here we have a constant and iron. They are made of two junctions. One is this junction, this creating this, and another thing is the constant and copper wire is also made another junction. Nice one. Okay, so what we have understood is if one of the junctions are maintained at the same temperature, the EMF will not be changed. So if the binding post at the voltage measure are the different, if these two temperatures, the binding posts are this, if they are at two different temperatures, to compensate for this extra EMF, we will make this kind of an arrangement where the constant and copper wire, wherever it is joining, it is not directly connected to the circuit. Instead, it is maintained at a 0 degree centigrade, just like this. Since these two are at the same temperature, we don't have this junction and this junction where the copper and this one are connected. Even though this is varying, the temperatures at this are varying, since the junctions which are forming with the two materials are maintained at the same temperature, there is no additional EMF which is being produced. This is one method of forming the thermocouple circuit. Okay, and the other way all around what we do in figure B, you can see in figure B, this can be safely used. Suppose if the temperature of this binding post, we call them as the binding post. If they are at the same temperature, we don't need to have another junction like this. We can directly, so you can see constant iron and constant and iron. So these two can be directly utilized on the binding post. So they are at the same temperature. We don't need to provide the compensation for them. So directly we can use this. Okay. The system got hanged.
Clear, sir.
What is trying to do? Yeah, no, the problem was my PPT got hanged. So now you can see that the thermal EMF in absolute millivolts for commonly used thermocouple combinations. So you may get a doubt, sir, what is the EMF that we can produce in millivolts out of this this particular temperature difference? You can see the temperatures, variations in temperatures, like temperature in degrees centigrade. The other temperature you can assume that to be 0 degrees, suppose. So that is the reason why for a 0 degrees temperature, that means one of the hot bead. So this is maintained at a particular temperature. This temperature they are mentioning. This is also always mentioned at 0 degrees centigrade. So minus 150 to 0, you are getting copper versus constant and minus 4.648. Okay, so that is a T-type junction. This T-type thermocouple, E-type, J-type, K-type, and S-type and N-type. All this, how much temperature or how much voltage it is creating? It's in millivolts. So you can see at minus 150 degrees centigrade, we've got minus 4.648 millivolts. How much small voltage it is creating? For example, we have 400 degrees variation. So you can see here 20.872 is 20.872 millivolts, 28.9 millivolts. Everything in particular in that range of this millivolts we are getting. So that much lower millivolts. Suppose for 1000 we are getting 76.3 millivolts of temperature. That is what we are getting. Okay, so the output voltage E of a simple thermocouple circuit is written in the form of R AT plus R BT square plus 1 by 3 TQ. This is the general form where A, B are constants. Okay, in general, the voltage created as a function of temperature will be in this form. Are you getting me? So what does that mean, sir? What does that mean? That means the relation that we are creating out of this relation between E and T. Whatever the data points that we are getting, whatever the curve we are getting, this curve we are having in the form of half AT plus half BT square plus 1 by 3. In a linear line only, but this will be in this way. In general, we will show the relation the most accurate way between voltage. Okay, so output voltage to the temperature is this. Clear? So this line can be determined. This trending line can be in any way. It can be a second order, it can be a third order, it can be a first order, it can be logarithmic, it can be exponential. So how do you follow these lines is dependent on you, right? So I will use a third order polynomial. That is the meaning. Shall I continue? Shall I continue for another 10 minutes? Is it okay?
Yes, sir, fine.
Yeah. So now let us move on to the temperature measurement by thermometer. From this, what you understand is how much the temperature difference, even though the temperature difference is high, the voltage or the potential difference that is created or measured is pretty low in order. So naturally, the lower the value, the smaller the value that we will get. That the sensitivity is smaller. So therefore, what can be done? People have thought of it. What can be done to actually increase the sensitivity of the instrument? That means for the same temperature difference, the temperature is TL and TH. The hot junction temperature minus cold junction temperature is same. But what can we do? This is TH and TL. Wherever TH is there, that is the same temperature, and TL is at the same temperature. So this is the hot junction. For example, the surface temperature of it. This is in a cold bath. Okay, this is all connected to a voltmeter to find out the voltage. Now, by connecting the thermocouples in a series, we call that instrument to be thermocouple. The instrument we call it as a thermocouple. What is the use of it, sir? So you can see here, because of the number of the series thermocouples, for each number of thermocouple, we are increasing the voltage by that much. See, the resulting total output voltage from a thermopile arrangement as shown in the figure is equal to the sum of junction voltage differentials. Okay, so it is the sum of junction voltage differentials of all of this. So thermopiles generally naturally have higher sensitivity compared to the thermocouples. Ultimately, it is the difference of TH minus TL, which is equivalent to the voltage value will be the summation of all of these values. So initially, when one thermocouple is used, for example, if you are getting 10 microvolt or 10 millivolt you are getting. Now, if you are using 3, then it will be 30 millivolts for the same temperature. So this is for 30 degrees variation, for example. For the same 30 degrees variation, you are getting 30. So the sensitivity of the instrument is higher compared to a thermocouple. Okay, thermopiles are therefore useful to get substantial voltage output even for a small temperature difference. Even though there is a small temperature difference, because we have so many thermocouples arranged in series, we are having good voltage. Clear? I hope you are clear. Now, temperature measurement by in parallel. So you also can do the same thing when we arrange the thermocouples in parallel arrangement. Thermocouples connected in parallel provides the average temperature value of the points on which each thermocouple is connected. Okay. So if you want to find out the temperature, average temperature value of the points of the where the thermocouple. So suppose you can see over here there is a particular box kind of a thing. You can see the dotted lines. So if you want to find out the surface temperature of each of that, we can connect them in parallel. See, iron constant and iron constant and iron constant, iron and constant. Because of this, these connections, the average temperature, the junction is this, where junction 1, junction 2, junction 3, they are maintained at the same temperature. And therefore, they provides the average temperature of the values of points on which each thermocouple is connected. Okay, 1 plus 2 plus 3 plus 4, whatever be the average value if you want to find. So in general, on a hotter plate or something, we don't get almost uniform temperature everywhere. There is a small change in temperature. Suppose you want to find out the average temperature of all of this, we generally connect these thermocouples in parallel, and that will give you the average temperature as a measure. Directly, it will give the average value of this. Okay, so in non-uniform temperature surfaces, we generally use thermocouples. You may ask, sir, what is the use of this? Anybody? In series, what is the use? Please answer. What is the use of thermocouples connecting in series? Are there anyone in the class or anyone left? What is that?
We are listening, sir.
Yeah. What is the difference in the two statements that I made? In series, the surface temperatures are same. pH is same. TL is same. So what it is does, for the same temperature difference, we are increasing the output voltage such that it can be measured easily. Okay. Whereas here, for finding the average temperature for a non-isothermal surface, if the temperature surface is not uniform, it has variation. Generally, we want to show the temperature of the body with one number. We connect these thermocouples as a parallel in parallel form, and whatever the value that we are getting out of it from this, whatever the output that we are getting out, that is nothing but the TH minus TC. No, so that TH is not the value of one surface temperature, but it is the average of all the junctions of the hot surface. Clear? It's not neither junction 1 temperature, neither junction 2, junction 3, junction 4, but instead it is nothing but junction 1 temperature plus junction 2 temperature plus junction 3 temperature plus junction 4 temperature by 4. That is what we will get out of this. Okay, so that is the thermoelectric effects. Now, the temperature measurement by electrical effects, this also comes under thermoelectric effects only. So this part, this one is basically about your RTDs and thermistors, and then we have the last topic as radiation, which we can complete in the last session, like in the Friday class. I think definitely complete this part. So we can stop at this point of time. If you have any doubts, please go ahead and ask me. If you have no doubts, then okay, I'm stopping.
Yeah, sir. Like for series, we are just using it if we have a very less difference, or we can say voltage. Like we are to we can't measure the like small voltage difference, so we are using a series thermocouple, so that we can like we have a significant voltage.
Exactly.
So this is the only use, sir?
That is the only use. That is what, because the sensitivity can be increased, no?
Yes,
see,
sir,
30 volts, 31 volts we can measure, but if it is 0.1 millivolt to 0.2 millivolt, the instrument which is measuring itself will have a lot of errors. The lower the values, generally the measurement system will not be able to trace it. So that's the reason why you see any measuring instrument or any variable. For a medium range, the cost will be okay. So from a pressure gauge, from 1 atmosphere to 5 atmosphere, you will get very medium value. If you want to have it from some negative pressures to 1 atmosphere, the cost will increase, because that includes very low sensitivity, very high sensitivity, and as the sensitivity increases, your cost will increase. Therefore, generally what we try to do here is scaling up the output voltage. That is what we are. At the same temperature, we are trying to upgrade the voltage differences. That is what. So one question I have. So if two dissimilar materials are connected, why EMF is produced? What is the electromotive force that is created? Why? So suppose if there is one material, why it is not being produced? That you can check it out. Those who have got interest and all. If a single material has a temperature difference at two ends, only heat energy will be transferred. If two dissimilar materials are produced, then we are actually providing both electrical energy as well as heat transfer is happening simultaneously. Both of the things are happening. Because of this, electrons will try to move, and that is what is creating. Because of this temperature difference in these two materials, some electrons are tends to move from their positions. That is the reason why you have this voltage potential difference. Is what is happening. Okay, you can have a look at it now. The important question is, suppose whatever the device that I have shown to you, that is my data log. Where is the temperature compensation? Where is the 0 degrees that you have produced? So we need a cold junction temperature. How it can be made in a data log? You can find out and let me understand that. That is the work that I'm doing. Have you understood my questions? Anyone? One person, please try to answer this. As I have shown you in the PPTs, we need a hot junction and another cold junction. Therefore, we are actually doing it. When it comes to a data logger, we don't have a cold junction, right? We are not having ice or water. How we are doing that? It's by electrical means that I'm telling you. But how it is made? Okay. So those who has interest, they can explain it to the class in the Friday's class, because I don't have time to explain. We will finish the class, and after that, on 10 to 11, 11 to 11:10 also we can explain that. So anyone who is having interest, please do that. Okay. So any questions apart from this? Okay. So if you don't have no questions, then to wind up the session. Thanks for attending the class. I will meet you again on Friday. All right. Take care.